Have you ever stopped and just wondered how a computer, a machine that only gets ones and zeros, can possibly understand something as complex as Python or C++? I mean, it really does feel like magic. But today, we're going to pull back that curtain and look at the beautiful, elegant math that makes it all happen. Okay, let's start with a feeling every single programmer knows, that dreaded syntax error. You miss one little semicolon, you forget a bracket, and bam, the computer immediately complains. But how? How does it know the rules you were supposed to be following? The answer, it turns out, starts with a very special kind of program. And here it is. Meet the compiler. You can think of it as the ultimate translator. Its entire job is to take the code that you and I can read and turn it into the binary language that the machine actually speaks. But, and this is the important part, before it can even start translating, it has to do a really crucial first step. It has to check if your code actually follows the rules of the language. And for that, it needs a perfect, totally unambiguous definition of what those rules are. So how in the world do you define rules for a computer? We can't just use vague guidelines like we do in English. We need something super precise, something mathematical. And this is where we get into the world of what are called formal languages. To build one of those, we have to start with the absolute smallest pieces you can imagine. It all starts with a symbol. Seriously, this is the most basic unit there is. Think of it like a single letter or a character. It's kind of like the indivisible atom of our language. By itself, a symbol doesn't mean much, but it is the foundation for absolutely everything else. Okay, so you take those symbols and you group them together into an alphabet. This is just the complete finite set of all the symbols we're allowed to use. So for a binary system, right, the alphabet is tiny, just 0 and 1. But for a programming language, it's way bigger. It's all the letters, numbers, and special characters you see on your keyboard. All right, now we can actually start building something. When we take symbols from our alphabet and line them up in a sequence, we create what's called a word, or what programmers usually just call a string. These are the sequences our machine is going to read and analyze, one symbol at a time. And that brings us to the language itself. A language is just the complete set of all the valid words you can possibly form from that alphabet. I want you to think about this. Your entire C++ program, from the very first character to the very last, is really just one very long word in the C++ language. And the compiler's first job is to figure out if the word you wrote is actually a member of that very exclusive club. So, here's the million-dollar question, right? It's impossible to just write down a list of every single valid program. There's an infinite number of them. So how do we create a compact set of rules for an infinite language? And then how do we build a machine that can actually check those rules? Well, it turns out computer science has two really elegant and deeply connected answers. The first answer is that we have to describe the patterns of the language. And for this, we use an incredibly powerful tool called regular expressions. You can think of them as a tiny little language of their own, designed specifically for one thing, describing patterns in text. Okay, so check this out. Regular expressions are built from just 3 basic operations. First, you've got union, which is basically a fancy OR. Then there's concatenation, which just lets you stick words together. But the real magic, the real power, comes from this little thing called the star operator. It means 0 or more repetitions of something. And that little star is what lets us describe patterns of any length. With just these 3 simple building blocks, you can define unbelievably complex structures, everything from what an email address looks like to the syntax of an entire programming language. Okay, so describing a pattern is one thing, but we still need a machine that can recognize it. And that brings us to the other side of the coin, a theoretical machine called a finite automaton. I want you to imagine a really simple machine. It has a start state, and it reads your code one character at a time, almost like a tape head moving along a conveyor belt. Each character it reads tells it which state to jump to next. And when it gets to the very end of your code, it only has one question to answer. Did it land on a special accepting state? If the answer is yes, your code is valid. If no, you get that syntax error. That's it. It is a beautifully simple model for how a computer checks your work. Now, there are 2 main flavors of these machines. Over on the left, you have non-deterministic automata, or NFAs. Think of these as being kind of flexible, almost a little bit magical. From one state, a single input could send it down multiple possible paths. It's like it can explore many possibilities all at once. This makes them a lot easier for us humans to design. But then on the right, you have deterministic automata, or DFAs. These are rigid, predictable. For every state, And every input, there is exactly one next step. No guesswork, no ambiguity. And this makes them incredibly fast for a computer to actually run, even if they are a little harder to design upfront. And this right here brings us to the most brilliant insight in this entire field. You've got these two things that seem totally different: regular expressions for describing patterns and finite automata for recognizing them. And as it turns out, they're not different at all. They are two sides of the exact same coin. This is the absolute key takeaway. Regular expressions and finite automata are perfectly equivalent in their power. Any language you can describe with a regular expression, you can build a finite automata to recognize, and the other way around. They're just two different ways of looking at the exact same thing, a regular language. And this isn't just some neat theory either. There's a really clever algorithm called the power set construction that lets us automatically convert one of those easy-to-design NFAs into a super fast DFA. This means we get the best of both worlds: a human-friendly way to design the rules and a machine-friendly way to execute them at lightning speed. But these simple, elegant machines, they can't do everything. They have a fundamental limit, a boundary of what they can compute. And knowing what they can't do is just as important as knowing what they can. So take a look at this language. It's any number of zeros followed by the exact same number of ones. So 01 is good, 0011 is good, but 001 is bad. Seems pretty simple, right? Well, a finite automaton cannot recognize this language. Why? Because a finite automaton has a finite number of states. It has no memory. It can't count up to 1,000,000 zeros and then somehow remember that it needs to check for 1,000,000 ones. It just doesn't have the capacity to store an unbounded number like that. This whole limitation is proven with something called the pumping lemma, which basically uses the pigeonhole principle you see here. Just imagine the machine's states are the pigeonholes. If you feed it a really, really long string, those are the pigeons, it eventually has to revisit a state it's already been in. It has no choice. This creates a loop, and once there's a loop, the machine can get stuck going around it over and over again. And that means it gets confused. It'll start accepting strings with the wrong number of zeros and ones, completely breaking the rule of our language. So let's bring this all the way back to that frustrating syntax error. It's not just the computer being picky, it's the elegant, logical conclusion of this entire process. A deterministic finite automaton, which was built from a regular expression, read your code symbol by symbol, and simply concluded that the word you wrote isn't part of its defined language. So what are the big takeaways from all this? Well, first, that compilers understand our code using the super strict rules of formal languages. Second, we've got two equivalent tools for the job: regular expressions to describe the rules and finite automata to enforce them. And finally, knowing that these tools have limits, well, that's what pushed computer scientists to invent even more powerful models of computation. And that kind of leaves us with one last fascinating question, doesn't it? If a finite automaton can't even handle something as simple as counting, what kind of machine can? What lies beyond these regular languages? Well, that's a story for another time. A story that involves things like push-down automata, context-free grammars, and the legendary Turing machine. Thanks for joining me on this one.